Hello, this is a test. If you can hear me, that would be good. Just let me know. But as of right now, currently, I'm just gonna try to speak flow of the thought, because I think that's the best way to do it. Jump in the conversation randomly. Um, what I never expected was becoming a physicist and then realizing, like, your whole life, wanting to get something, and then you realize you don't like that, or at least it's not as fun as you thought it would be. Um, and it was very it's weird because you try to get something for your whole life and you get there and it's complicated. It's not that it's complicated, it's just that it feels ungratifying. It feels open-ended, and it feels like you're going into a wall. But for now, let's talk about the difficulties of this. I suppose you can hear me, and if you can, then that's fine. I need to find and I need help with trying to get applications for the particle theory stuff, because I know it can be translated to code, but at this point, unfortunately, I'm gonna need like a little bit more assistance on the code wise, because I understand how to fragment things and how to make classes, but the current problem that I'm trying to do is trying to unify, at least within the computer science. Like I need to try to write what the problem is. And unfortunately, the problem is something that is a little annoying because computer science majors will just kind of look a little pissy. They'll be like, there's no such thing as like binary trees. They don't have an exact structure to them. They'll, well, code can't be made more efficient because of how the way computers are made. But that's a separate problem in physics. That has to do with how the transistors are being made, how the chips are made. But back to the thing that I was trying to communicate with the computer scientists. So we need to find a way, if there's anybody willing to listen, that we need to find a way to convert the particle theory stuff to code, but not just that. We need to actually build a circuit for that. And I have like a few propositions. So one of them is to build like what's I'm thinking could, and this has to do with the map of particle physics that we came up with a while back. So what we're going to have to do is we're going to have to actually build transistors in a new way. We're going to need to build transistors to accommodate this new information theory stuff. Um, Specifically, that things can be written and decomposed as just up and down. So how do we write things in terms of code? This is the difficult part. How do we write code that is efficient wise with transistors, that doesn't take too many transistors, but it has the qualities of having the required characteristics that we need for particle interactions? So I'm thinking the minimum amount of transistors should be 4. And this seems like we need to have like it's almost like dual processing, so we need to have 4 of these. So let's try to build a theoretical circuit component together. And that's what I'm trying to do right now. I just decided to go live with this because it's a hard process, and I kind of want you guys to see why this stuff is very slow. And here's my current model that I've been working on, but we need to improve this. So this is where I'm at, and this is sort of the limit for now. If there's any recommendations, so we need to have the components of up bar, down, and down bar. Another thing that we're going to need, that's going to be another challenge, is we're going to need to present the W plus, the W minus, the Z0 minus, and the Z0 plus. This component requires that we have, let me write down the rules. W plus is U bar. So you can visualize what's going on. Sarm singularity, that's precisely sort of what we're trying to do. Happy Wednesday to you. How am I? Not that well, actually. That's sort of why I'm trying to get this done. I'm trying to basically break the stress and request information from people that are true computer scientists, because the limit right now in terms of where I'm at is that we need an actual computer scientist, and I say that because I don't necessarily think they're better than physicists. I just think they're more qualified at having practice. I think physicists are more qualified to do computer science and information theory because of the stuff that we discovered with particle physics. But we need them simply for now to help us structure the information theory. So W minus is going to be the opposite. It's going to be U bar. D Z0 minus is going to be down bar. Z0 plus is going to be up bar. So you can already see that there's going to be some forms that we're going to start seeing. So the W plus is going to mean that we have processes. So if we ever want a this combination, which is a very important rule, all you need to predict anything in the entire world are these 4 chains. The Z0 plus, the Z0 minus, the W minus, and the W plus. The reason I waited so long to talk about this stuff is, thank you, absolutely. I need help now, and that's the problem. So let's describe the problem real quick. So as you can see, I was waiting to hold back on requesting information for how to code this because I was trying to confirm this not only in daily life, but also in terms of the theory itself. But I am satisfied enough to the point where I believe we should move forward and we need to actually advance this theory. So the way this is done is that we're going to need this interaction, the W plus. If we ever see this prediction, we're going to need one input on the upside and one input on the down bar side. And the output needs to get connected together. Do you get me? If they're connected, then that's a W plus. If we have a W minus, that means we need one up bar input and one down input. And we need to start to figure out how to make an efficient circuit. That's the first part. So there's multiple parts of physics. So we can't just give this to the computer scientists, because the problem that I explained earlier is that transistors are not laid out like this. They are not laid out like this. They're not laid out to be made into binary trees. They're not structured like this. Sort of RAM is structured like this, but even then, not really. So that's where we're at. So just to restate for those that are arriving, what we need is I need someone, probably an electrical engineer. So if you're an electrical engineer, give recommendations. Just make a TikTok and response and reply, and at me. We're going to need for this input W plus, and we need so there's two things. So there's multiple things that we need for the future of physics and the future of computation to get a hell of a lot faster. And we need these things. So what we need is we need an input to have these 4 binaries. These 2 binaries, which is technically up and anti-up. So this might be able to be represented as a 1. So what that means is we can have a full state here, and this is why we're trying to figure this out together. We're trying to do this together. So we can have 1 for up. We can have 0 for anti-up. We need a 1 bit for up, and we need an other bit for down. But I don't think that's necessarily because how do we represent the Z zeros? You can't do that if you have this allocation. If you have an allocation like this, well, if we try to represent a Z0 family tree, I'm trying to help explain the problem with physics right now, that we can be advancing computation because we discovered that particle physics will always loop. Because it will always loop, you can always predict things of the future at the macro scale and the micro scale. What really happened is that I discovered a while back that the standard model goes infinitely up and infinitely down. Can we do this on a quantum gate? It already happens every day. Every single moment of every single, instance, there's these rules, specifically the W exchanges, the most. These are kind of like the electrical exchanges. You can imagine them like that. These are the electrical exchanges because these are what we consider to be charge in physics. You exchange charges. But how does the exchange occur? It exchanges at a full charge integer values. Basically, even physics are messed up. No, we're not messed up. What happened is that we're done. We don't need anything else. Uh, at least we're done on the scale of research of information theory. So back to reiterate, we cannot represent our particles, our rule set, because the reason what okay, back, slow down. This then. What we need is a way to code efficiently the rules of particle physics because they predict everything in the macro scale. And yes, this is literally the maximum scale of performance. Yes, this is the fastest way you can compute anything because that's how the universe does it. The universe basically says that we are the. I am in your guest box. Oh hell yeah! Let me accept you. Thank you. Um, let's hope we can talk about this.
Now, are you trying to base it on the description of like macro scale? You're talking about the macro. You're talking about everything that we could physically observe, like all
So
events.
this is pretty cool about it. All events are always what's it called? They're in these rule sets. They're in specific, not any other rule sets. They're in these rule sets. You don't need this
Now,
stuff. This is just how to calculate it, but this is how it comes in terms of
yeah,
particles. This is the
I
macro
understand that.
aspect.
I'm
Yeah.
wondering what scale that you're working on. Are you working on the Planck line scale, or are we talking about events that are in the size of like the nuclei of atoms, like bosons and quarks?
That's what's beautiful about this, about the because we hit the quantum, because we hit the fundamental scale of reality, we don't need to be there anymore. We don't have to. So that's why we use electrons in terms of computers. You
Yeah,
don't
because the
have. It's like
electron is a
simply
lot larger than the nuclei of an atom.
it's a lot smaller.
No, it's no the electron field is its circumference is the
True,
whole
true. Actually,
yeah, because technically it's a probability density that we're measuring.
yeah. So I'm saying that we don't need this. So we don't. You don't need to use. You don't need to use anything small anymore. You could. This can actually be done with big circuit elements. So that's like the cool thing about physics. We've hit the point that transistors no longer need to be small. We can actually make efficient computations if we can code it correctly. So theoretically, there could be water computers, and there could have been back in the past. Basically, use an aqueduct, that's your power source, and you put in
Yeah, I've seen
plugs
the
where you
studies
want the
on
water
that.
to split. Yeah.
Yeah, the water gates.
So that's what's cool about it. We've hit the limit where we need to just focus on the code theory. And that's what we're trying to do right now. We're just trying to write the code.
But it's still prudent that we utilize less energy for higher efficiency.
Oh,
And
absolutely. That's why we try to use
and
electrons.
we could even pull out even quantum energy. We could go even smaller on the scale if we were able to encode information at that at the quark like the quark field. Like if we were able to manipulate that, that would like it's a it's a size and energy problem.
And that's the thing that's sort of like the double-edged sword. We could go smaller, but now it's we don't need to. It's sort of like making uh sorry. It's like an efficiency problem. You get me? It's like optimization. You could go smaller, but we've hit the point with the particle physics that if you want to go smaller, you actually owe energy because the scale of our universe requires everything to be at the scale of electron and bigger. That's where we're at. So I would not recommend as a physicist that we go smaller. It's actually going to cost you more energy So we're actually at a pretty good
Yeah,
optimization. The
yeah,
electron happens to be
that
the
is
perfect
true
unit.
because it takes more energy than what we get out of the systems we have now. Even quantum systems, you have to pump so much. Just the energy that needs to be pumped out of the system is energy technically put in, like
So you're
pulling the
talking about heat. Yeah,
vacuum,
absolutely.
bringing the heat energy down, and shielding because you don't want no stray electromagnetic energy getting into the system and flipping the qubits. I've worked with these systems. I have quantum. I have the. Uh, I'm signed up for the IBM quantum computers.
Oh hell yeah, that's cool. I'm trying to make this not need quantum. I'm trying to basically help boost classical computers.
So you're saying that you could write it on a set of rules that is efficient enough that it could still computate all if it's written on the formula that you're proposing, right? So that's
Yes.
what you're saying.
So yeah,
A
I'm trying to help just basically improve processing power, not memory. I guess it's like I'm trying to help RAM get more efficient. Not just RAM, but code, because code is written very inefficiently right now. I would like it to be written more efficiently. If we can start writing in terms of the fundamental processes, I think everything would go a lot smoother. Basically, write for the quantum computer now so that when we do get them, you can just send your code over to IBM's quantum computer and it would be
They
equal.
have that. It's a composer. You're able to
They have a
actually write
compiler?
out. Yeah, you could write out compilers and everything, and they simulate it. But you could actually have it ran on the quantum systems. You take a ticket out for your project. I've done quantum teleportation. I have I've measured teleportation on it and uh, quantum entanglement.
Okay. Would you have any recommendations the for classical? Because I'm trying to introduce this to regular computer science. Because I feel like we're wasting a lot of stuff right now for just basic operators. You get me? If we can try to, because I think the quantum stuff, I agree with you. That's actually very fascinating. I didn't know there's compilers for it, but I'm trying to help, I guess, aid both sides by having this structure written now. Because I don't think they've yet recognized that the fundamental particles have this chain, have these qualities. There's no work in the literature that says the Z0 even has uh, particles within them. I propose they do, and by all verifications, by every particle that I have checked from the particle data group, they work. So I'm just trying to use it for the code writing, I guess.
Are these gates? What are they running on? Single electron gates?
No, I think these should probably be. We're trying to make this right now small scale, so we're gonna make. I'm trying to make this testable for now. So I'm gonna make these out of JFETs, not MOSFETs,
Hmm.
because my
Okay.
professor said that JFETs are zero energy waste or something. So I'm trying to find out the least amount of transistors I would need. You get me? So we need. I think I need this 4 units. So I can have like one up for here. So for Z0 plus, we have both ups on. And we need to somehow have it come together, and that comes out the output of Z0 plus. Let's bring up one example of a particle reaction so we can see how the particles represent macro scale
Oh,
events.
okay.
I think,
You're wanting to build AND gates that or AND gates or whatever. You want to build a system that's describing the interactions at the fundamental, right?
I think you're right. I think you're actually exactly correct. We can use gates for that. You're right. Okay. Okay. Good, good. Let's use gates. Okay. Okay, let's write that. Let's change our
Yeah, because we
ideas.
could have it as one as an end gate, and then okay, it would be you're describing it as up, down, right? On both of them.
So there's only for every single particle can be described as decompositions of yes, of the up and down.
Yeah, so you got it's four gates. So technically it could be two gates because if we're describing up and down, and that's the two sets, what is the other two for? I get the up down for the first two.
Oh, so here's the weird thing about that. So great question. The weird thing about that's going on is that, so let me go back to this. We need these because we explained earlier that unfortunately the z zeros cannot be described in terms of just a single path. We can't just have this as transition on and off. We need these both as unique transistors that can both go on or off.
So that, yeah, that'd be an AND gate. That could be on
Okay.
or off.
Okay, thank you. So zeros can be described as and. Thank you. And the W's need to have, so for W minus, for example, it needs to have an anti up and needs to have a regular down. It has to. It has to have those two
All
if it
right.
wants to be one of these.
So we could just describe it as one gate is permanently open and one gate. Well, so are we doing three gates then technically? It would be one that's open, one that only needs to be in the on or off position, and then one that's closed, right?
Let me explain one more thing, at least just the bigger scale, about why we're doing this. Find it. Let me explain why this speeds up calculations, specifically if I can find one particle example that is simple to do.
Because I've seen a program that does it in a matrix style, and it has a integer variable in each individual coordinate on the plane, right? You have your plane, you have your grid, and each square on that plane has a number system that could be changed only in the up or down. And what they call it, like the push and pull system. And all interactions of basically fundamental physics has been simulated through just push and pull, up and down values. And
Yes.
it is correlated to the adjacent squares to each, in um like pushing on a screen and how you're causing a deviation within the screen where that pressure is, um like we say it's 15, it causes the surrounding coordinates to change its value to become equilibrium to the system.
Okay, so you're going into the actual engineering of the, or at least the